Hi, it's Dr. J again. In today's video, we will be looking at special relativity and in particular using the relative velocity equations. Let's consider two spaceships moving away from the Earth in opposite directions, each at a speed of 0.75 c. At what speed will each spaceship see the other moving away? So you can see here the scenario. We have our Earth and then we have our two spaceships moving in opposite directions from the Earth. Now, if these were at non-relativistic speeds, we would just say, well, one is negative of the other, so we would add the two velocities together. So we would say 0.75 c take away negative 0.75 c, which is equal to 1.5 c. Big problem here. We can't have speeds that are greater than c. We have two postulates and it would violate one of these. So the first of the postulates is no law of physics can identify a state of absolute rest. That's not a problem. The speed of light will always be c no matter what the motion of the light source or the observer. No object can travel at faster than the speed of light regardless of your frame of reference. So that's going to be a problem. We actually have two equations that are on our formula and constant sheet to calculate the relative speed between objects that are traveling at relativistic speeds. Remember that relativistic speeds are talking about when we are at fractions of the speed of light. In everyday circumstances, we don't need to worry about that. So if we're talking about 100 kilometers per hour, that is not a relativistic speed. So we don't need to worry about these equations. Okay, so let's have a look at the equations straight out of the formula and constant sheet. So there's no need to memorize, thank goodness. So we've got u is equal to v plus u dash divided by 1 plus v times u dash over c squared. And the other equation is u dash is equal to u take v divided by 1 take away u times v over c squared. As with all equations, you need to know how to use them in order for them to be useful. So the best way for me to define the variables so that I can recall them, because this is a memorized thing, is I write my variables down in alphabetical order, u, then v, and then I write u dash. U is the velocity of object 1 with respect to the observer. V is the velocity of object 2 with respect to the observer, and then u dash would be the velocity of object 1 with respect to object 2. Okay, so it makes it really easy to remember. So u, v, u dash, object 1, object 2, object 1 with respect to object 2. Okay, let's try using these equations. Here is my scenario again. And what I'm going to do is, the first thing I'm going to do is I'm going to define which is object 1, which is object 2, and which is the observer. So object 1 here, object 2 here. So I'm looking to find the velocity, the relative velocity between object 1 and object 2. And here is my observer. Okay, next, let's write down our u, v, and u dash. And I actually write this down. So object 1 with respect to observer, object 2 with respect to observer, and then object 1 with respect to object 2. And then let's pop our numbers in. Okay, so object 1 with respect to the observer is 0.75 c, and it's left. Object 2 with respect to the observer would be 0.75 c right. Now we need all these velocities to be in the same direction, so let's make them all left. And then we have object 1 with respect to object 2, which is what we're looking for. So the equation I'm going to use is the u dash one. Never try and rearrange these. Always make sure that the thing you're looking for is the quantity that's out the front. So I've got u take v over 1 take u times v over c squared. Let's pop those numbers in. So I've got 0.75 c take away negative 0.75 C divided by 1 take, and I've got 0.75 C negative 0.75 C divided by C squared. Now you'll see that that C and that C will cancel with those down the bottom there. So what I end up with is 1.5 C, I'm going to run out of room here, about 1.5 C divided by 1 plus, because that negative and that negative cancel each other out, I've got 0.75 times 0.75. And I then end up with 0.96 C. So let's put it in standard notation. So 9.60 times 10 to the minus 1 C left. Okay, so we've used that first equation. We're now going to move on to using the second of these equations. Okay, so same scenario. This time I'm going to say that this is object 1, this is object 2, and this is the observer. The equation I'm going to use is that u is equal to v plus u dash over 1 plus v times u dash over c squared. Now to define again, so I've got u, v, u dash. So I've got object 1 with respect to observer, object 2 with respect to observer, and then object 1 with respect to object 2. So I'm looking to find object 1 with respect to the observer, so I'm looking for u. So object 2 with respect to the observer, well, the observer we consider to be stationary, so the Earth would be moving to the left at 0.75 C. So 0.75 C left, and then object 1 with respect to object 2 would also be 0.5 C left. Okay, let's put that into our equation. So I have 0.75 C plus 0.75 C over 1 plus 0.75 C times 0.75 C divided by C squared. Again, we can cancel those C values out. So I've got 1.5 C over 1 plus 0.75 times by 0.75. And that will again give me 9.60 by 10 to the minus 1 C left. So there we have used the two equations. That's the end of my video. Thank you so much for listening. In the next video, I will do a 2020 WACE question which uses these equations. Again, if you could subscribe to Dr. J, that would be great. Thank you.